Hyperbolic functions are functions defined in terms of the exponential function. These hyperbolic functions have properties similar to those of the trigonometric functions. Hyperbolic functions are important because they appear in the nature in various forms. The function hyperbolic cosine is defined by setting its value at x to be e to the x plus e to the negative of x divided by 2. The red curve shown here is the graph of hyperbolic cosine. It is called a catenary curve because it represents a freely hanging cable. Such freely hanging cables, of course, appear in many places in nature, and therefore this is an important function. This has also been used by architects. The Gateway Arc of St. Louis, Missouri is a famous example. The architect Eero Saarinen used an inverted hyperbolic cosine curve to design this Gateway Arc. The famous Catalan architect Antoni Gaudí has used hyperbolic cosine extensively in his work. Here is an arc and a spiral staircase by Gaudí. The arc is an inverted hyperbolic cosine curve. And here is yet another look at the Gateway Arc of Eero Saarinen in St. Louis, Missouri. The function hyperbolic sine is defined by setting its value at x to be e to the x minus e to the negative of x divided by 2. The graph of the hyperbolic sine function is the blue curve shown here. It is everywhere increasing. It takes the value 0 at x equals 0. For x positive, hyperbolic sine of x is positive. For x negative, hyperbolic sine of x is negative. The function hyperbolic tangent is defined by setting its value at x to be hyperbolic sine at x divided by hyperbolic cosine at x. In terms of the exponential function, this can be written as e to the x minus e to the negative of x divided by e to the x plus e to the negative of x. The blue curve is the graph of the hyperbolic tangent function. It's a bijection from the real line, from the set of real numbers, to the open interval from -1 to 1. The hyperbolic cotangent function is hyperbolic cosine divided by hyperbolic sine. The names of the hyperbolic functions, hyperbolic sine, hyperbolic cosine, hyperbolic tangent, and hyperbolic cotangent, indicate that these functions are closely related to trigonometric functions. This is indeed the case, even though the definitions of these functions appear to be completely different. The hyperbolic functions enjoy properties very much similar to those of the trigonometric functions. For example, hyperbolic sine at negative of x is negative of hyperbolic sine of x. Hyperbolic cosine at negative of x is hyperbolic cosine at x. This is just the same formula as we have for the trigonometric functions sine and cosine. Then we have hyperbolic cosine squared minus hyperbolic sine squared is 1. For the trigonometric functions, the corresponding equation was that cosine squared plus sine squared is 1. Here we have hyperbolic cosine squared minus hyperbolic sine squared is 1. This slight difference means that we can use hyperbolic functions in places where trigonometric functions do not necessarily work to solve certain problems. Hyperbolic cosine at x plus y is hyperbolic cosine at x times hyperbolic cosine at y plus hyperbolic sine at x times hyperbolic sine at y. Similar formula as for the corresponding trigonometric functions. Hyperbolic sine at x plus y is hyperbolic sine at x times hyperbolic cosine at y plus hyperbolic cosine at x times hyperbolic sine at y. Let us take a look at how to prove this central formula. Hyperbolic cosine squared minus hyperbolic sine squared is 1. So I claim that hyperbolic cosine squared minus hyperbolic sine squared is always 1, and the proof uses just the definitions of these functions. So hyperbolic cosine squared minus hyperbolic sine squared is e to the x plus e to the negative of x divided by 2, and that's squared minus e to the x minus e to the negative of x. divided by 2 and that squared. Now we simply expand the brackets. We get from the first term e to the x and that squared plus 2 times e to the x times e to the negative of x plus e to the negative of x and that squared. Observe that e to the x times e to the negative of x is of course 1. So this first term is really e to the x and that squared plus 2 plus e to the negative of x and that squared. From the second term we have e to the x squared minus 2 times e to the x times e to the negative of x plus e to the negative of x and that squared. And of course everything divided by 4 when we expand the brackets. Here the terms e to the x squared and minus e to the x squared cancel out. And so do the terms e to the negative of x squared and minus e to the negative of x squared. So we are left with, in the numerator, 2 times e to the x times e to the negative of x minus 2 times the same. E to the x times e to the negative of x is just 1. So we are left with 1/4 of 2 plus 2, which is 1. And this proves the formula. Here are some more hyperbolic identities. Hyperbolic cosine squared of x is hyperbolic cosine 2x plus 1 divided by 2. Hyperbolic cosine 2x is hyperbolic cosine squared of x plus hyperbolic sine squared of x. And hyperbolic sine squared of x is hyperbolic cosine 2x minus 1 divided by 2. Hyperbolic sine 2 times x is 2 times hyperbolic sine of x times hyperbolic cosine of x. These hyperbolic identities are very similar to the trigonometric identities, and all these formula follow by direct computations based on the definitions. Simply insert the definitions of the hyperbolic functions in this formula, expand the brackets and simplify. One gets these formulas by straightforward computations. To summarize, we have defined the hyperbolic functions by the following expressions. Hyperbolic cosine of x is e to the x plus e to the negative of x divided by 2. Hyperbolic sine of x is e to the x minus e to the negative of x divided by 2. Hyperbolic tangent of x is hyperbolic sine of x divided by hyperbolic cosine of x. And hyperbolic cotangent of x is hyperbolic cosine of x divided by hyperbolic sine of x. These functions are important, foremostly because the graph of hyperbolic cosine is the catenary curve. Here is the church Sagrada Familia, which is still under construction after 100 years of starting the construction. The church uses lots of hyperbolic and parabolic shapes. The architect here is Antoni Gaudí. In this building, Casa Mila in Barcelona, Gaudí has used graphs of the hyperbolic cosine curve in many places. The building is absolutely magnificent. And here is yet the Gateway Arch of St. Louis, Missouri, architect Eero Saarinen. Inverted catenary curve.